In this lecture, today we are going to design a one-way RCC slab. What are the parameters given? Room size, effective dimensions are given 3 cross 7 meters, M20 FE415, and design method, it is by limit state method only. Now we have to see the ratio of L by B, length as well as width. When L by B ratio is greater than 2, we call this a one-way slab. It is already mentioned on page number 10 of IS code 456-2000. Now, how to calculate the value of assumed D? It is span by 20, which is already given in IS code so far. So suppose this span is the shorter span, because one-way slab, shorter span is always deflecting more and giving more maximum bending moment and considering 1 meter width only. So that will be the maximum depth is 150 mm. I am considering the overall as 150 and effective is say 120 mm. So our calculation will be based on now overall depth 150 and effective depth as 120 mm. We will go for load calculations. Dead load 0.15, always 1 meter width of the slab, 25 into 3. Mind it, always when we are talking about the width of a slab, whatever type of slab it will be, the width will always be taken as 1 meter. Live load, being a residential building, we can consider 2.5 into 1 meter is the width, and this is in kilonewton per meter square. Similarly, floor finish as usual we are taking as 0.5, total comes out to be 6.75, and design load will be 1.5 times this W, and WD comes out to be 10 point something, so I am rounding it on higher side at 12.0 kilonewton per meter. Now the span is 3 meter, UD is 12 kilonewton per meter as we have taken over here. Calculate the maximum bending moment WD L square by 8 and shear force WD LE by 2. It comes out to be 15.0 kilonewton meter and 18 kilonewton only. Now with the help of these parameters of maximum bending moment and the shear force, first we will go for the depth calculations. You know the mu max is equal to RBD square. For Fe415, R is equal to 0.138 into FCK, it is already taken as 2.76. And being a slab, it is always to be taken as 1000 mm. Substituting the value of this, converted this into Newton mm by multiplying by 10 to the power 6, and D required is 73.3. We have already provided D as 120. D as already 120. Now calculation for the main reinforcement. But one thing that we have to keep in always mind, that main reinforcement shall always be parallel to the shorter span and placed in the bottom of the slab. So suppose this is the shorter span, this is the longer span. Main reinforcement is placed like this, and distribution placed over the shorter span, it will be like this. Then we'll go for calculation of the area of steel for the main bar, and we'll find that this comes out to be, using the empirical formula and substituting the value of XU max, FCK BD, we are getting the area of steel as 370 mm square. Rounding it on the higher side, I am getting as 400 mm square. Considering 10 mm phi, then the area of steel can be calculated, area of one bar divided by the total area of steel, which is given as 400 mm. And it comes on 196.2 mm center to center. इसको round off on the lower side, I am considering this as 150 mm center to center. As I am reducing the spacing, means definitely the area of steel actually increases, Under such circumstances, we'll have to see two more things. One, the checking for the spacing and the actual area of steel. Now we'll go for calculation of the spacing. We have seen as per the IS code, you must see that the spacing of the main bar should not be greater than 3 times effective depth of the slab or 300 mm, whichever is less. 3D means 120 into 3 or 300 mm. So our spacing is 150 mm. So we can say our design is already safe. Now 3 times 360, 300. Ours is 150, which is less than this. So we can say our design is safe. Okay. Now we have already seen we have to calculate the actual area of steel because the spacing has reduced to 150. So calculating the actual area of steel, it comes out to 523.6 mm square. Of course, which should be more than 400 mm square as we have already seen previously. So our design is of course going to save. Now, once this main reinforcement has been calculated, we have to go for the distribution steel. As per the IS code, distribution steel will be 0.15% of gross cross-sectional area, 0.15% of B into capital D. 225 mm square, rounding it out to 250 mm square, using again the same bar of 10 mm and find out the spacing. It comes out to be 314 point something mm center to center. उसको राउंड ऑफ किया है, it comes out to be say 200 and 300 mm center to center. Again the condition for the spacing of the distribution bar. Under any circumstances, this spacing should not be more than 5 times effective depth of the slab or 450 mm, whichever is less. So it is 5 times the 120, that is 600 or 450. Our spacing is 300. So our design spacing is okay. Now we can next go for applying various checks. First check is the check for shear. We have already seen that the shear force is 18 kilonewton meter, and the code says that check for shear K times tau C should always be greater than tau V. Now tau V is equal to V upon BD. V is 18 into 10 to the power 3. B slab 1000, 20 it becomes 0.15 Newton per mm square. From the actual area of steel that we have already provided 523.6, then we have calculated actual PT and it comes out to be 0.84. For M20 and FE415, table number 19, page number 73, interpolating we can find out value of tau, so it comes out to 0.58 Newton per mm square. Now find the value of K. K is nothing but, as per the table given on page number 72, value of K up to 150 comes out to 1.3. 1.3 into 5.8 should always be greater than tau V BT, that is tau V. So it is 0.75, it is 0.15, much more safe. So we can say for shear it is safe. Now we go for check for LD, that is development length. 1.3 times M1 upon V plus L0 should always be greater than LD. Keeping M1 as 15 into 10 to the power 6. As usual, V is 18 into 10 to the power 3, and this comes out to be already, and this formula is given on page number 44 of LD. We have calculated and it comes out to 986. LD, this formula which is already given over here, it is to be increased by 60%. That's why 1.2 is to be increased by 1.6. It is 470.1 mm. Now we have to see under any circumstances this should always be greater than this. So 986 point is greater than this. We can say our design is safe. Now last check, let's check for deflection. As according to the rule, modification factor into 20 must be more than actual span by actual depth ratio. Modification factor can be calculated by percentage of steel that we have already found out so far previously, and then using figure number 4 and page number 38, we can find out the value of modification factor. It comes out to be 1.1 multiplied 20 should be greater than actual span by actual depth. So 20t should be greater than 20. We can say our design is safe. Now here L section is given. This is the main bar placed at the bottom of the 3 meters length of 10 mm bar at the rate of 300 mm center to, it should be taken as 10 mm bar at the rate of 150 mm center to center. This distribution steel is again 10 mm fire at the rate of 300 mm center to center. Alternate bars are bent up and its spacing will be definitely comes out to be 300 mm center to center. The total depth is 150. Effective depth right from here to here is 120. These are the supports. We have already taken the effective span and need not to go for support with otherwise we have to take into consideration the effective span by considering the width of the support or effective depth, whichever is less. That's over and all about the design of a one-way slab, larger one-way RCC slab. I think this is more than sufficient and we can conclude this design by showing the diagram over. That's over and all.